All right, let's dive straight into this explainer. Picture this high-stakes scenario. Your brand new mobile game, it just got featured on the App Store. This is literally the moment you and your team have been waiting for.
Traffic spikes exponentially. You go from 100 concurrent users to 100,000 users in just 10 minutes.
Your traditional Amazon RDS database hits 100% CPU. Your connections max out entirely. And then the absolute worst happens. The game crashes. You are losing money, you are losing momentum, and you are losing players by the second. But hey, what if I told you there's a world where this panic doesn't even exist?
Section 1. The paradigm shift. Serverless NoSQL.
If you had built this game on Amazon DynamoDB, your users wouldn't have noticed a thing. No downtime, no lag, because it's fully serverless and feels instantly fast no matter the scale. But to really grasp this, we need to completely shift our mental model. You don't have traditional tables connected by complex foreign keys here. Instead, you just have three simple things: tables, items, and attributes. Think of a table simply as a bucket. It's the core container that holds all your unstructured data. Inside that bucket, you have items. An item is basically just a single record. If we stick to our game example, a single item would be one player's entire profile. And finally, we have attributes. These are the specific data points living inside an item. Things like their username, their high score, and their current inventory. And really, that's it. Table, item, attribute. It's an incredibly streamlined structure.
Section 2. The core engine, partition keys.
So, how exactly does DynamoDB give you single-digit millisecond latency, whether you have 10 items or 10 billion items? Well, it all comes down to the partition key. Every single item must have a primary key. When you write data, DynamoDB takes that partition key, runs it through an internal hash function, and uses the output of that math to drop your item onto a specific physical storage server. And that physical server? That's called a partition. Think about that for a second. DynamoDB does not search a massive hard drive to find your data. It uses the hash to mathematically calculate exactly which server holds your item, and it goes straight to it. If your table grows too big, DynamoDB just quietly adds more partitions in the background and spreads the data out. That, my friends, is true infinite horizontal scaling. To implement this correctly as an AWS developer, you design your access patterns using a composite key. And that's just your partition key plus a sort key. Imagine a game leaderboard. The partition key could be the game ID, and the sort key is the timestamp. DynamoDB stores all the items with the exact same game ID physically close together on the very same server, automatically sorted by the timestamp. This means you can instantly query for the latest scores without any heavy lifting.
Section 3. The traps, where developers fail.
Listen closely, because this is where people mess up, and it's a massive pitfall if you're taking the AWS DVA-C02 exam. Trap number 1, running a scan operation instead of a query. Let's slow down here, because the difference is absolutely critical. A query efficiently goes straight to the exact partition using a key. A scan literally reads every single item in the entire table up to 1 megabyte at a time, throws away what it doesn't need, and then gives you the result. It is incredibly dangerous. A single scan can consume your entire database throughput in 1 second and just crash your application. Always, always design your tables to use a query. The second trap is the hot partition. Let's say you build a voting app and 90% of your users vote for option A. All that high traffic has the exact same partition key, which means it is all hitting the exact same physical server. That single server gets completely crushed, and DynamoDB throttles your requests, throwing a provisioned throughput exceeded exception. So what's the solution? You must design high cardinality partition keys. All that means is choosing a key with a vast number of unique values, like a unique user ID, for example. Doing this evenly distributes the traffic across all your partitions, keeping your database healthy and blazing fast. Section 4. Managing read and write capacity units. How do you actually manage the capacity and the cost for all this speed? Well, you do it using read capacity units, or RCUs, and write capacity units, or WCUs. Let's break down the reads. One RCU gets you one strongly consistent read per second for an item up to 4 kilobytes. But by default, DynamoDB uses eventually consistent reads. Because it replicates your data synchronously across 3 availability zones, if you read data immediately after writing it, you might hit a replica that hasn't fully updated yet. If you absolutely must have the latest data, you request a strongly consistent read. But watch out, That strongly consistent read costs twice as many RCUs. It's a double cost penalty.
So, the crucial point here is choosing the right capacity mode. If your traffic is totally unpredictable, you use on-demand capacity. It scales instantly and you just pay per request. If your traffic is predictable, you use provisioned capacity with autoscaling to save money. But what if you get a sudden, tiny spike? Don't worry, DynamoDB has your back with burst capacity, retaining up to 5 minutes of unused capacity to absorb the shock.
Section 5. The next level. Event-driven architecture.
Imagine a player buys a powerful new sword in your game. You need to update their inventory, send them a confirmation email, and unlock a new achievement. Doing all of that synchronously, that's going to slow down the entire game. Instead, you build a perfectly decoupled flow using DynamoDB streams. Here's exactly how it works. Step 1. The item changes in DynamoDB. Step 2. The stream instantly captures the before and after image of that item and drops it into a time-ordered log. Step 3. You connect that stream directly to an AWS Lambda function. The Lambda wakes up, sees the change, and asynchronously sends the email and unlocks the achievement. Your primary database stays instantly fast and completely unbothered.
Section 6. The 3 rules of NoSQL.
All right, let's lock this down with a rapid-fire recap. Rule 1. DynamoDB achieves single-digit millisecond latency by hashing the partition key to instantly locate the exact physical server holding your data. Rule 2. Never use a scan operation on a large table. Seriously, always design your access patterns to use efficient query operations. And Rule 3. Prevent hot partitions and throttling exceptions by choosing high cardinality partition keys. This will evenly distribute your read and write capacity units. I want to leave you with one final, firm warning. DynamoDB is not a drop-in replacement for a relational database. If you try to build complex SQL joins in DynamoDB, you will fail. In NoSQL, you design your table for the exact questions you need to ask, not just the data you need to store. So the next time you're architecting an app, ask yourself, are you just storing data, or are you designing for infinite scale?